Okay, so if you looked at the posted examples, you may have even printed them out. We've already done the first three. Number 4, it's time to add in springs, right? All the ones we've done so far in the examples and in the practice questions, the springs canceled out. So it's time to add in a spring. So example 4 says a 0.23 kilogram frictionless cart, so we're still not adding in friction yet, just springs, travels along a horizontal track and collides with the spring with a constant of 155 newtons per meter. If the spring is compressed 6 centimeters, how fast was the cart moving initially? Okay, so initially my cart is out here, right? And it's moving this way with some speed that we don't know. And when my cart's out here, my spring is just hanging out minding its own business. It's in what's called its equilibrium position. The cart hasn't touched it yet, so the spring isn't compressed at all. But now the cart is eventually going to come and hit the spring, and it's going to begin to compress the spring. So sometime later, the cart will be here and the spring. So the spring will be compressed some distance. And the question says it compresses the spring 6 centimeters. So the x final will be 6 centimeters, which of course we have to change to meters, so 0.06. And when the springs compress this much, the cart has come to a stop. So the v final is 0. Okay, the question also tells us that the spring constant, which is the K, is 155 newtons per meter, and that the mass of this cart is 0.23 kilograms. And it wants to know what's the VI. We're looking for VI. So you write down your energy equation, 1/2 mv initial squared plus mgh initial plus 1/2 kx initial squared equals 1/2 mv final squared mgh final 1/2 kx final squared plus E lost. So still no E lost because it said frictionless. So initially there's a speed, that's what we're looking for, but there's no height, or whatever the height is, like it's on a table. The height, it might be 3 meters off the ground, but it's not changing. So we say, okay, that we're going to call whatever height it's at height 0. Okay, so it's going to cancel out in both spots because it isn't going to change. Initially, the x is 0, so this term goes. Afterwards, once the spring's compressed, there's no speed because the box keeps compressing it until it eventually stops. No height still. There is an x, we have it, and there's no E lost. So this time our two terms are 1/2 mv initial squared equals 1/2 kx final squared. All right, the m's don't cancel this time, but the halves will. And you're looking for k. No, you're looking for vi. So divide both sides by m. So vi squared will equal kx final squared divided by m. The k was 155 newtons per meter. The x was our 0.06 meters, and remember that's squared. And the m was 0.23 kilograms. And what you get is going to be vi squared, and then you're going to take the square root. So vi squared is 2.426 meters squared per second squared. And so when you take the square root, 1.5576 meters per second. The two most common mistakes. People write this square down on the x, but when they type it in their calculator, they forget to punch it in. The second one, you'll get to this number, 2.426, and you'll forget that it's a v squared. You'll forget to take the square root, because it seems pretty reasonable that it could be a speed, right? So watch the squares and the square roots here. They're just mistakes looking for a place to happen. Okay, so that's number 4. Number 5, also on that sheet, your sheet looked a little different than my sheet because I edited it before I put it up for you. Number 5 is also with the spring. It says a 4-kilogram cart. This time it's attached to a spring. Okay, so this time, here's the spring, and the cart is actually attached to it, whereas up here it was coming in and compressing it. But here, this cart spring system is attached, and it's just hanging out, minding its own business in what we would call its equilibrium position, where it would be if we weren't doing anything to mess around with it. But of course, we're going to do something to mess around with it to make it more exciting. So it says it's sitting on a frictionless, again, no friction, horizontal surface. And then it's pulled out a distance of 1.6 meters. So we're going to pull it out here to a distance x equals 1.6 meters. And sometimes this is called the amplitude. It's pulled out to an amplitude. If you think of a wave, the amplitude of the wave is its height. And I'll come back to that in a minute. Okay, now so I'm pulling it out here and I'm holding it. It's not moving. So my V out here will be 0. And now I'm going to release it. And as I release it, it's going to pick up speed, pick up speed, pick up speed, hit its maximum speed here. And as it does that, the x is going to get smaller and smaller and smaller and smaller until it gets to 0. So this is the spot where it's going to have its maximum speed. And it tells us that in the question that its maximum speed is 6 meters per second when it gets back to its equilibrium position. Okay, now it's not going to stop here. It's going to keep going, and it'll end up compressing the spring a distance in the opposite direction of negative 1.6 meters, where the V would be 0. And if there's no friction, it'll be like a mirror image. It'll keep oscillating back and forth so that it actually will look like a wave, and that's why this is called the amplitude. This would be how far it is above its rest position, how far below. So it would be, okay, but we'll get to amplitudes in waves very soon. So the question wants to know what's K. And so we're going to use our energy equation. 1/2 mv initial squared, mg h initial, 1/2 k x initial squared equals 1/2 mv final squared, mg h final, 1/2 k x final squared, plus E lost. So it said frictionless, so there's no E lost. So it doesn't really matter which one you call the initial. I'd probably call this my initial and this my final. So if this is my initial, there's no speed out there. But in whatever the height it isn't changing, so we'll just call that height equal to 0. And there is an x, so this term stays. In the final, in the middle here, there's a speed, no height, no x. So my two terms are 1/2 k x initial squared equals 1/2 mv final squared. Again, the m's will cancel. This time I'm looking for k, so divide both sides by x initial squared. So the m was 4 kilograms. The final speed, 6 meters per second squared, divided by 1.6 meters squared. And again, where the errors will happen is you will write these on your questions, but you'll forget to type them in the calculator. When you do this, though, and type in all the squares, you get 56.25 newtons per meter. Okay? And so your practice problems today are going to have springs in them. And they'll all be horizontal surfaces, so there'll be no MGHs, and they'll all be frictionless, so there'll be no E lost. We'll save that for tomorrow.